So this is today we are going to have the third presentation. So in this I have actually two. Like first is again we go back to the reinforced soil walls. So we look at 2-3 issues. In the second one, it's a brief presentation on gabion retaining walls. So today in this, many things we have covered in the first presentation, but certain aspects, a little more detail, we will cover. Like one is, we are going to look at the limit state design, once again, in probably a bit more detail. Then again, the connection strength issues. And third is drainage, which was not covered in the first presentation. Now, coming to the limit state design, see earlier we used to do what is known as the allowable stress or working stress design. So here mainly we have the loads, then we have the strength, and the principle is like we divide the strength by a factor of safety so that it is less than the applied loads actually. So here the factor safety accounts for many things, we calculate the loads, but we are not sure, like there is always a variability, uncertainty. Similarly, if we calculate the strength, for example, the bearing capacity, there are many uncertainties, like we are not 100% sure what we are calculating is right. Then in the method itself, like for example, we have a bearing capacity formula. So what is the surety that it's true? Like we don't know, a lot of assumptions are there to factor for that. Then again, a consequence of failure, like if something failure occurs, what's its impact? Like, so many things. Then the factor safety is based on our experience actually. Like, is it 2, 2.5, 3? See, over a period of time, we have got that experience. From that, the code specify the factor safety. Then another is like to control deformations. Like probably earlier, like for example, we may not be calculating settlement explicitly, but you calculate the bearing capacity and apply a large enough factor of safety, then probably the settlements will be like, normally our objective is the stress is within the elastic limit, elastic range. So the settlements are also controlled like that. See, only problem is like we have a factor of safety, everything is lumped into this number. Like, so then people realize probably this is not the right way to do it. So then we went for the limit state method. So like, what is a limit state? Like we are putting a limit, okay. We should not go beyond this limit. It is not acceptable. There are different limit states. Like one is like a ultimate or collapse. Like our structure itself is collapse. Like then third is, okay, structure doesn't collapse, but it deforms too much, or if vibrates too much, like it doesn't satisfy the function it was built for. Like then third is like durability. Okay, like it is stable, like serviceable, but then it corrodes or like degrades. Then there is too much maintenance like that. That also doesn't serve the purpose like that. And again, normally we can see as our society progresses or the profession develops, our focus shifts. Like initially, like our concern is to prevent failure. The next stage, like to ensure serviceability, then it goes to durability, like that, controlling. Then finally, again, it goes beyond that. Now we are like worried about sustainability. That is another issue. Then if you look at the Euro code, the ultimate limit states defines many. Like one is equilibrium. So here, one example is in the retaining walls, the overturning. So this actually it's a movement as a rigid body. Like it is like there is no stress actually. Like it overturns as a rigid body. Failure like this is called equilibrium. Then it is called STR, stands for structure. Like a structural failure. Like for example, like if it's RCC retaining wall, like bending moment, shear force, basically it's a structure which deforms, fails like that. The strength of the structural element comes into play. Then Geo stands for geotech. Like a bearing capacity failure is a geotechnical failure. The ground fails, soil fails. Then UPL is uplift. Then this is hydraulic, heave, erosion. Like suppose it says scour in front of the structure, that is a hydraulic failure. So these are all the limit states. Then again in this, like how do we handle the uncertainty? Like the limit state methods, like if it is in the loads, there are many uncertainties. Like so what we calculate maybe the average load, then we can take a characteristic, okay, with a probability like that. Then again there is uncertainty, we can take partial load factors. So that means the nominal loads are multiplied by factors. Then there is uncertainty in the material strength, like whether it is strength or modulus, there are uncertainties. So to account for that, we take partial material factors, like the material properties in the construction, because we are providing a certain dimensions, but then there is a tolerance to that, like that. Then the model uncertainties, that means we use a calculation method, always there are assumptions, these are all approximate, like that. So we have partial material factors. Another is consequence of failure. Like if it is a small unimportant structure, like for example, a small retaining wall for a landscaping, okay, even if it fails, there is not much of a problem. But if it is a highway retaining wall, which retains a road or an airport or a railway track, failure occurs means there are large consequences. So probably we should use a larger factor there. So here the principle, we have the loads, then strength again, then partial load factors, partial material safety factors, then there is a partial factor for the consequence or ramifications of failure. So we formulate the design criteria, like the resistance, we divide by these factors, and the loads multiplied by the load factors, and all the factors are greater than 1. Then we satisfy this inequality, though. So we ensure that we are within those limits actually. So now we come to the reinforced soil walls. If you look at the load combinations for walls like that. Again, like there are different loads, like dead loads, live loads, like earthquake. So they don't act like simultaneously. So there are load combinations. So mainly we have to see what is the worst load combination. And this could be different for different things like that. So in the BS code, there are 3 load combinations like A, B, C, and each they are given the partial factors we can see. Typically for load case C is for serviceability, which means all the partial factors are 1. So if you look at load combination A, so here the self weight, it is multiplied by 1.5. Similarly, any surcharge like sloping surcharge 1.5. Similarly, like if you have a traffic load, again all 1.5. So this actually gives maximum reinforcement tension and maximum bearing pressure. Like that. So this is load combination A. If you look at load combination B, the vertical forces like self weight, this one, like it's multiplied by 1. Like that. Even if the pavement like a dead load surcharge, it will be multiplied by 1. But behind in the retained fill, the earth pressure, it is multiplied by 1.5. Similarly, live load multiplied by 1.5. So in this part, this is the reinforced soil part, there is no live load. We can imagine the situation like suppose in that particular lane, there is no traffic, but behind there is traffic like that. So this combination is critical for sliding because your disturbing force is maximum, it is multiplied by 1.5, whereas your resisting, it is multiplied by 1 only. So similarly, internal sliding, then for reinforcement, pull out also. The third combination is load combination C. So basically this is for serviceability. So mainly for vertical settlement and post-construction creep strain. So here all the load factors are 1 like that. Because actually like serviceability is a like everyday situation. So we look at, okay, what are the regular loads which are acting every day? In the collapse, we look at a factor so that we want to avoid that collapse. Like that. Then coming to the material factors, it specifies like soil material factors like the angle of shearing resistance, effective cohesion, and drain cohesion. Then for the load case A and B, then load case C, like angle of shearing resistance and rain coefficient, the material factor is 1. So probably the assumption is, okay, our methods are reasonable. Like, but if you look at effective coefficient, there is a large factor safety, like 1.6. So what it says is, like, okay, if I am going to use effective coefficient, for example, in sliding or bearing capacity, we have to be very cautious like that. So we apply a large factor. Then coming to the reinforcement material factor, that means on the long-term design strength, there are various factors. So here there are several, like actually the BS gives a very detailed procedure in the annex. So we have to follow that. If you are using metallic reinforcement, there is a certain procedure, there are certain factors. If you are using geosynthetic reinforcement, again, there are different factors like creep, insulation damage, then durability, like that they give detail. Then soil reinforcement interaction factors, like there is two types of interactions. One is in direct sliding, then second is in pull out. So here these are the partial safety factors, like 1.3, 1.3. Then partial safety factors, like one is to be applied to the ultimate bearing capacity. Then the sliding resistance. So when we check for bearing capacity, what do we do? Like we calculate the ultimate bearing capacity. So like on that, we apply a factor safety of 1.35. Then the loads, actual loads, we have multiplied by 1.5 actually with the load factor. Then we compare these two. Similarly, sliding along the base, like it is 1.2. Then another factor, like the factor for the economic ramifications of failure. So here we look at what are the impact of failure. Like, okay, if something fails, the consequences are not much, then we take a factor of 1. So it also gives examples like small height retaining walls, like where failure would result in minimal damage or loss of access, like that. Then medium also, like embankments and structures where failure would result in moderate damage and loss of services, like 1. Then high is like bridge abutments, like structures directly supporting important roads or railways, like that, buildings, etc. So here, if a failure occurs, the consequences will be severe. So we take a factor of 1.1. Okay, that was about the limit state design. It was just to explain what are the load combinations A, B, C, then what is the logic behind the different partial load factors and partial material factors. Then again, as I mentioned earlier, the connection between the reinforcement and the facing is an important aspect actually. And especially in India, like we have a lot of failures actually. Some of the, if you look at the failures, like many were used to the poor connections. Normally what people are trying to do is like, okay, because here it's a very competitive market, like the company which gives the lowest price, normally they get the job actually. So like the reinforcement, like it is, many things are codified actually. You cannot go beyond a limit because the code specifies what should be the strength, pull out, length, everything is specified. You cannot go beyond the limit. Similarly, the facing, again, like you cannot cut too much on that. So like any system, there are certain gray areas actually. Not everything is very specified or like people don't check thoroughly like that. So here sometimes we are tempted to take advantage of, like we are trying to experiment, innovate. In that process, our objective is mainly to reduce cost, but sometimes you end up in problems like failures. Like, so this one area where we need to be very cautious. Like now, what are the loads acting on the facing? Again, BS code gives this, like due to the horizontal earth pressure and the reinforcement tension. Like horizontal earth pressure is action, then which is resisted by the reinforcement. So this. Then weight of the superimposed facing units. Like at the lower level, over that, the height of facing is there. So the vertical weight is imposed. Then vertical shear forces due to the relative settlement between fill and facing. So like fill is soil, like normally if it is properly compacted, there should not be much internal settlement actually, because when you, if it is compacted to the probably 95% modified proctor, Then even if you place 5 or 10 meters of soil above that, it should not ideally settle. The internal settlement comes like in an earth ramp, probably like 50 meters or 100 meters. There you can expect probably. But here shouldn't happen. But sometimes what happens? Our compaction is not proper, like especially the lift thickness. Like ideally, we should compact in 200 or 250 layers. But sometimes what happens? Like you put 1 meter of soil, then you run the roller. So in that, only the top 0.2 meters gets compacted. Below that, it is loose actually. Then over a period of time, like especially if it gets saturated, there is a collapse settlement. So at that time, there is a relative movement between the facing and fill. So when the fill settles, your geogrid is pushed down, then it applies a vertical load on the facing. Then any externally applied loads, for example, like a vehicle impact, then differential longitudinal settlements. Like when the facing settles, there is a differential settlement, there are distortion. So this induces additional stresses on the facing. See now again, like we have seen this, the BS defines what are the connection loads. Like again, this is like what is the exact load coming at the connection, it varies. But the code says, okay, like we are not concerned what are the exact forces which is coming at the connection. So I actually designed the connection for this loads. So at the top, like a tie-back wedge method, which is applicable for extensible reinforcement. At the top, it is like 75%, bottom 100%. That means all facings with movement capacity or movement at the connections. But if you have a stiff face, like for example, like a full height panel, then it should be 100% of the reinforcement tension. Coming to coherent gravity, which is applicable for inextensible reinforcement, then suppose we have a flexible face, for example, like a metal U-shape elements. Like one of the earlier facings, which probably we don't use now, it's like a metal sheet, like thin sheets bent into this U-shape like that. So it can accommodate a lot of movement. So we have this distribution. The top up to a depth of 0.6 times height, it is 75%, then 100%. Then this discrete concrete panels, like which have a height of about 1.5 meters and width of 1.5 meters. Again, it is from 85% to 100%. So if we have segmental block walls and full height panels with no movement at the capacity at the connections, it has to be 100% of the reinforcement tension. So like we don't have to worry about how do I calculate the tension. Like once we have calculated the tension and the reinforcement, we can take these values as the load at the connection, then design for that. Then in the case of segmental blocks, which are used with geogrids or even geotextiles, there are two possibilities. One is a frictional connection. So this means the reinforcement is just put between the layers of blocks. Or we can have a positive connection. So here there are different mechanisms, like basically it's friction between, one is between geosynthetic and the concrete block surface. Then some blocks are hollow with aggregate infill. So there is interlocking or friction between the geosynthetic and the aggregate. Then third is like sometimes the concrete surface is not plane actually. There are some shear keys or what we call like a tongue and groove kind of thing. So the reinforcement goes around that. So that may give an additional resistance. Then here positive connection, again there are different ways, we will see that. See, one is geosynthetic concrete friction. This is more or less concrete surface against concrete surface. So the geosynthetic is put between that. Only here you can see a lip. So geosynthetic goes slightly down. So this may give a slightly, when you try to pull out, it may give slightly more resistance. Then you can see this aggregate, this hollows, it will be filled with aggregate. So when the normal force comes from the aggregate, it develops good amount of friction actually. So again, different types of like blocks, we can see this hollow spaces which are filled with aggregate. So in this actually, here the bottom, it will be aggregate. When the next block comes, probably top, it may be concrete actually. So both ways. So another is, I mentioned about this shear case, like uh, like geosynthetic is not at all layers, like probably the spacing maybe about 0.6 meter. So in between, again, concrete should have good shear resistance. It should not slide. For that, the shear case is given. So when the geosynthetic is put here, like you can imagine, it comes like this, then take a king, then again goes down, then next block sits on that actually. So compared to a plain surface, this may give slightly more resistance. Then we can have positive connection, different types of arrangements, this type, and we can have this type of connector. And again, it may not be applicable for all geosynthetics. So this type of connector we can only use for what are known as rigid grids, like high density polyethylene, like a tensor grid. If you try to do this with a polyester grid, it will not work actually, because here we don't have this junction strength like that. For this to work, first the transverse ribs should take the load, then transfer to the longitudinal strip, which is possible only if the junctions are strong. In this case, the junctions are very poor. It is only the PVC coating which holds the junction like that. So if you try to put this type of connection, it will not work. Then another way is like this, like we can see there is a vertical slot in the block. It's a fairly large block. Then the geogrid goes through this hole, then wrap back into the fill. You can see this like. So this is like a wrap around, again a positive connection like that. It doesn't depend on the friction. This is a positive like that. But then this is possible only in probably in a large blocks we can do that. And the geogrids are not continuous. It's are like a strips, like narrow width strips.